Next conference is about Beyond 5, which is an example of IPCEI-induced collaboration. The goal of Beyond 5 is to build a completely European supply chain for radio frequency electronics, enabling new RF domains for sensing, communication, 5G radio infrastructure, and beyond. The consortium involves 40 partners, 14 large groups, 11 SMEs, 4 RTOs, and 11 universities. Ericsson Research and Lund University took part in this project. So thank you, Fredrik and Liang, to shed some light on this project. Thank you very much.
Thank you. So let's see. Right, so thank you for the kind introduction. So Liang and myself, we are very much engaged in this project activity where we target a low-power 5G access point. I know it was worded as a 5G low-power base station before, but I think access point is a better wording since a base station is quite complex and this is more geared towards the radio functionality. And as you may remember from François' presentation, this is part of the Beyond 5 project, the quite big-scale Excel 2019 activity involving many partners spanning across Europe. And we have, I think, in total 6 demonstrators, and this is one of them. So this is what we would like to talk about. As a starting point, just to set the scene, let's start with how deployment looks today. We need to cover a whole variety of different scenarios when we deploy a network, stretching from rural areas into very dense urban environments. And of course, we need to have different methods, different approaches in order to make this efficient. But there are some common denominators. That is, we would like to raise the overall network capacity at the same time as we can preserve the cost. I mean, we cannot explode, we cannot densify everywhere. We can only do it where it makes sense. So we have listed here some examples of methods we use. I mean, we try to find new spectrum, we use multi-carrier, you can go for MIMO, you try to increase sectorization, and then over here, you might even find opportunities to densify by having smaller cells and also cater for indoor solutions. Because in the end, what we like to get rid of are difficult users. Difficult users mean that you have a poor radio channel. You consume a lot of radio resources for the network. So if we can get rid of bad users, turn them into good users, it's much better. And if we then, like I mentioned here, we try to go for new frequencies. You're all aware of 5G, of course, and what has happened to 5G compared to 4G is that we have been able to get more frequency bands into the system. One of the big steps was to get millimeter wave into the equation. So these are frequencies typically ranging above 24 gigahertz up to some 40 plus gigahertz, and there you will find new deployment today, especially in the US where this is happening as we speak. Now, when you move up in frequency, this will have implications on the hardware realization. First of all, you need to combat the increased propagation loss. That's a problem when it comes to reach, the cell size, etc. How do you do that? Typically, you increase the aperture instead. So you increase the aperture of the antenna system to compensate for the free space path loss. What you would end up with is basically an array, an antenna array. Still, each patch has to cater for the lambda, the wavelength, so you will have multiple antenna ports collaborating. This will also enable MIMO, so many pieces coming together here, and you're able to direct your beams to specific users or make use of the propagation environment, like we do in digital beamforming, for instance, to make a certain transmission to a user. Now, as you can see here, this simple picture is when we go for these larger scale systems, when you ramp up the antenna size, you have more ICs. You put more silicon into play when it comes to these systems compared to the ordinary classic ones. And this is something for the topic today, right? How do we make use of advanced technologies in order to cater for such a system? And if I'd just like to say a few words before we go actually into Beyond 5, what have we done here historically at Ericsson in Lund? Well, we have worked on SOI technologies for many, many years, looking into our roadmap, see how they can really fit our product plans. And we have tried to explore this from different angles. So just showcasing an evolution here, stretching from the 22 or 28 nanometer F2SOI attempts here some years ago, all the way up to some recent designs in 22 nanometer, where the integration has just increased. You can see the number of radios here put on the dies is really getting quite impressive. This is one approach. Of course, depending on what technologies you integrate in the end, you may have a different architecture. But this is one approach we have looked into. So how does this then relate to Beyond 5? Well, besides the technology that is shared in Beyond 5, in this demonstrator, we don't target the regular grid, how the network is looking today. Instead, we target a use case which is much, much smaller in cell size. How do we address users being placed in confined environments? In this case, an indoor environment. So we scouted a bit in the beginning of the project, what kind of demonstrator should we have for this? And we concluded, what about an airplane? Let's go for an airplane scenario. You have all been in planes. You know that when you embark the plane, all of a sudden you have to turn into Wi-Fi. It's very, well, some carriers today offer maybe 3G connections and 4G connections, but it is a bit cumbersome. You cannot really stay with your normal subscription. You have to do a lot of things. This we would like to get rid of. So working together with Airbus, which is an associated partner in Beyond 5, we thought, what about if we can demonstrate a 5G system in an airplane that is still viable from a cost perspective, still viable from a building practice perspective, so you can fit the airplane without all the hassle of bulkiness, etc. So it's a quite challenging use case. We target 39 gigahertz as the carrier frequency, so on the upper side of millimeter, you might say, then our frequency bands, and the channel bandwidth is kept rather small. That is due to that we don't envisage, too hefty amount of capacity needed in this environment, and that we also need to be able to integrate it to a building practice that makes sense. So we need to really go for low power here, and then we didn't really want to expand the requirements too much. The reach is 10 meters, so quite small. You can envisage a real low power node here. And in the demonstrator, we believe we can connect some 4 UEs to the access point. That is what we target. The demo will happen end of next year outside Munich, in one of Airbus facilities, so in Ottobrunn, outside, just a short trip from Munich, where they have this mock-up. So it will be a full-blown 330 cabin, where we will bring our equipment and hopefully be able to showcase a MIMO system using this piece of equipment. I think Liang will talk a little bit more about that when it comes to the algorithms and how we implement that. But if I continue to stick with a radio system, this is how it looks. This is what we plan to demonstrate. Going from left to right, you have the antenna array, 16 patches, double polarized, so 32 antenna ports in total. Quite many RFICs supporting all those ports, and you see how each RFIC looks like here. So the radio chip, we have 4 transceivers, and we have a clock generation, data converters, and an I/O interface. And you also see the partners, who is developing what. So it's a truly collaborative project here, where Ericsson here in Lund, we are responsible for the I/O development, how we ship bits from this chip into the digital part, which in this case is an FPGA solution. Now you might wonder, why do you go for an FPGA solution, not an ASIC solution? It's due to the workload, I would say. What we plan to do is to explore algorithms, etc. I would love to have an ASIC here, but when you run these kind of EU projects, you don't have time to do everything. So we had to go for an FPGA-based solution, which also means that we need to develop an interface here that is generic and off-the-shelf, more or less. So it's a GTH standard-based interface. But we have also developed the proprietary interface. that we will publish shortly. Right. And just to showcase a little bit, the developed ICs. This one over here was our first test chip. This is on 22 nanometer, as you understand, and it was taped out roughly a year ago. We have the different building blocks here, and they are being measured in lab as we speak. The first one to be measured is, of course, the probed, where we can probe the subsystems here, meaning the high RF systems. So we do probe measurements on the RX and TX, and now we're about to measure the bumped version, meaning we have it in a package, and that goes for the data converters and the I/O. And this we plan to publish hopefully within months. We should be able to have more published results about this. Then taping out really soon. Actually, the tape out is on Monday, but it will happen. There is a small delay, but the plan was on Monday, but I got some input earlier today that it may not happen on Monday, but yeah. And this is the chip. So this is when we put everything together. We have the 4 TRXs, we have the I/O, as it looks now, communicating with FPGA. So quite hefty chip. It's some 24 square millimeters or 22, some in the vicinity of 22 square millimeters. And there you see the schematic, how it's made. And one issue with these kind of projects is that they are a bit confidential. I mean, when you have a joint undertake like this, quite many partners, there is confidentiality. So that's why I have not presented performance numbers, because I cannot do that. But we will disseminate the results, and that will be available to you. But many of you are actually part of Beyond 5. I mean, you work for ST, you work for Lund University, you work for Soitec and Ericsson, and you're part of Beyond 5. So please download, our deliverables, and you will have access to the parameters and the performance, etc., what we have measured so far. So just reach out. And there are papers coming along. For instance, this one describing the radio front and the receiver that was published now at MicCon just 2 months ago or so. So quite recent. So feel free to reach out, and we'll be happy to share. Right, so now I give the word to Liang.
Thanks, Fredrik. So before I dive deep into the digital part, I would like to revisit the big picture of the entire system, because I think it's important. As Fredrik already mentioned, for fully digital beamforming, for each of the antennas, we have RF chain, we have dead converters, and we have digital front end. And then all those signals will gather to MIMO processing to do digital beamforming. Although, as mentioned in the demonstrator, we will use FPGA for fast prototyping and then for easy debugging. But in the future low-power deployment, we envision multi-chip or multi-die solution. One of the important questions in multi-chip or multi-die solution is how we distribute processing among different dies. This is a question without a trivial answer. And one of the important facts is the data exchange between different chips and dies. And here I just have some numbers at different stages of this system. So for example, if we put the boundary here, that we have a dedicated analog chip and then pure digital chip, then the chip I/O need to support around 300 gigabit per second. That is huge. And then if we can integrate some of the digital functionality towards the RF chip, we can reduce the I/O rate significantly and save the corresponding power. And then we believe that the FD-SOI is one of the technologies can enable this type of integration. Of course, to achieve overall energy efficiency, we need to consider different facts like operating at different technology nodes, and we also need to consider the scalability and the flexibility of the system. So that's from the system level. And then another question, actually, if you would like to integrate the digital functionality, can you handle this massive complexity of MIMO system? Actually, when several years ago, when we started to promote MIMO technology, the very first question we got is that, can you process all signals from all the antennas in real time and in an energy efficient way? No one believed MIMO. Of course, the answer was yes. Otherwise, I would not stand here and talk to you, right? And the key thing is to really explore opportunities at different design levels, from system to technology. For example, you would like to explore like the features in the cabin, the MIMO features to have simplified algorithm. We need to explore that level parallelism to improve throughput, and we explore, for example, the body bias in FD-SOI to tune as an extra knob to tune the energy efficiency. And then this is exactly what Beyond 5 is. We have expertise from the entire value chain, from system end users, system providers, circuit designers, to semiconductor technology providers. So we can do this cross-layer optimization. And then here at Lund University, we have been applying this type of method into the mass MIMO processing, and we ended up with some chips that just a showcase. This was the first mass MIMO chip in FD-SOI. It supports 128 antennas, so it's huge size matrix we need to process, and it's real-time processing, 300 megabit per second. It consumes, if I remember correctly, around 50 milliwatts. Just as for reference, we also built the first mass MIMO testbed, like 8 years ago, and then the processing was distributed over around 50 FPGAs. The power consumption is around 2 kilowatt compared to this. And of course, then we are confident we can do this in FD-SOI. Then we move forward. We implemented even more complicated algorithms for mass MIMO, and this is the second chip. It supports more users, like 16, and then we have adaptive algorithms to provide better performance, and is in a similar cost. So after these two successfully chips, we're becoming more aggressive. So we say, can we integrate even more? Of course. We have the third chip that was published in 2021. So it's not only MIMO processing, we also integrated OFDM, synchronization, resampling filters into one chip. So that was all from my side, that we already saw that FD-SOI can actually support efficient processing for both RF and analog, and then give the final punch to Fredrik for a demo.
Yeah, I think the final punchline is actually that we will have a demo roughly 1 year from now, or in December next year, and we will stay very transparent leading to that date, and hopefully we can have a really nice dissemination activity, and be happy to share more info with you along the way. So thank you very much for your attention.
Thank you.